Hello, in this video we're going to be going over exponential word problems. Now your homework 12 is going to have a lot of different types of homework problems that involve exponential word problems, but this video will not cover all of them. This video is going to cover the more basic version. There are other types of word problems that use words like doubling or having, like half-lives, and those types of problems will be covered in the next video. So don't panic if you see a word problem and you don't know how to answer it after you've watched this video, because it might be something that I cover in the next video. So that said, let's dive into some of the more basic types of word problems that you might encounter involving exponentials. Here's an example from the common version of the homework, where you're given this cute little story about a restaurant owner selling macaroni and cheese, but really all we care about is the formula that he has developed that models, I guess, demand for his dishes. The Q of T represents the number of orders for the dish, and the only other variable in this is T, which represents time. So the first part of the question says, what is the approximate total number of dishes? So they're asking what is Q that he can expect to sell on day 8. So that's our time. So all we're doing here is we're plugging 8 in for Q. Or we're plugging 8 in for T. So we're going to take Q of 8, which will be 400 divided by 1 plus 4e to the negative 0.2 times 8. And all we do here is plug this into a calculator. Be careful when you do that. Just make sure you've got parentheses in the right places. For instance, you'll need parentheses around your denominator when you plug this into a calculator. And you should come out with a decimal number that's approximately 221. Now, since we're talking about the number of dishes he's going to sell, you'll need to round this to the nearest whole number, even though it doesn't specifically say that. Actually, never mind, it does. All right, so for part B is a more conceptual question. They're asking at what number of dishes does he expect his sales to level off? Here's what we're asking in this question. Functions that contain exponentials always have a horizontal asymptote. We've discussed this before. So your function might look something like this, where it's increasing, but then it'll eventually start to decrease and it'll have a horizontal asymptote here. Off the top of my head, I actually don't know what this function is going to look like. Maybe it's a function that increases like this, but eventually, at some point, there's going to be a horizontal asymptote. And that's what this question is asking. Where will the sales level off? Where will our horizontal asymptote be located? So to answer this question, we need to take a closer look at the function itself. So when we're talking about a horizontal asymptote, we're talking about our function leveling off at some point. What we're really asking for is, what is the y value at some really far out x value? So maybe x is 1,000 or t is 1,000. What would our y value be getting really, really, really close to? It'll never exactly equal it because you can never reach your asymptote, but it'll get really, really, really close to some value. So we're going to basically estimate this using a logical process that starts by looking at t. So t, we're going to imagine that this is getting really, really, really big, approaching infinity even. But since it's kind of hard to imagine infinity, let's think of some huge number, like 1,000,000. If we put 1,000,000 in for t, then negative 0.2 times t will also be some really, really, really big but negative number. So something in the ballpark of negative 200,000. So e to the negative 200,000, what is that going to be approaching? When you have a negative exponent, remember what it does to your base. It pushes your base into the bottom of a fraction. So that's really going to push our e down to the bottom of a fraction, like this. And since it was 4 times e to the negative 200,000, we'll essentially have 4 over e to the 200,000. This e to the 200,000 is going to be some enormous number. So 4 over some enormous number, let's just call it 10 billion just for fun, is going to be such a small fraction that it's basically 0. So this whole piece of our function is basically just going to be getting closer and closer and closer and closer to 0. And that's because we have a negative exponent. So as our exponent gets bigger, our e gets smaller, so this whole number is getting closer and closer to 0. So if what I circled in black is getting closer and closer to 0, essentially our entire function is getting closer to this, 400 divided by 1, which is just 400. So our horizontal asymptote is going to be at 400. The moral of the story here is that the logic we're using is a little bit convoluted, but the answer ends up being relatively simple. The negative exponent is going to send that whole piece of our function to 0. And so what you're going to end up with as your horizontal asymptote is just the 400 divided by 1, just those constants. So we're going to do a very similar type of example one more time. In this example, we're dealing with a contagious virus, and in part A, we want to know looks like we're going to have to do a little bit of advanced work. So in part A, they're asking us, imagine this is blank. In part A, they're asking us if blank people will have been infected by day 4. This essentially is its own question. So we need to figure out how many people will have been infected by day 4. So we're plugging 4 in as our time. So we're going to take Q of 4, which is 1500 divided by 1 plus 152, e to the negative 0.3 times 4. Just like in the last example, we're going to plug this into our calculator, and you should get approximately 32. Now again, we're estimating here. You're going to have to round this to a whole number because when we're counting humans, we're going to count humans in whole numbers. The next part of part A says how many days will it take before 1,125 people have been infected. So this is a totally different question. I don't know quite why they worded it this way, put 2 questions into one. But here, this number they're giving us, 1,125 people, that represents Q. That represents the quantity of people that have been infected. So the 1,125 number replaces Q. And our job now is to find T. So this is going to be a little bit more complicated because we have to solve for T, and T is deeply buried within this function. So we're going to have to go through a lot of steps to get that T by itself on one side. First of all, I'm going to multiply both sides of this equation by the denominator, 1 plus 152 e to the negative 0.3 t. And both sides. And the reason we do this is so that the denominator cancels on the right, and that brings our, the part of our function that contains t, that brings it up into the numerator. All right, moving on. Now we're going to divide both sides by 1,125. So on the left, I'll just have 1 plus 152 e to the negative 0.3 t, and on the right we'll have 1500 divided by 1125. Now, continuing our mission to get t by itself, we're going to subtract 1 from both sides. Minus 1. And next, divide both sides by 152. So this is getting uglier and uglier by the minute every time we make a move. So now we have fractions inside of fractions, but don't worry, our calculator will take care of all of this. Okay, now we're trying to get this t by itself here. So we next have to get rid of the e. We get rid of exponentials by doing the inverse of an exponential, which is a log. And since natural log has a base of e, natural log and e are inverses. So we'll take the natural log of both sides, which will cancel with the e on the left. So we will now have negative 0.3 t equals the natural log of 1500 divided by 1125 minus 1 over 152. And then our very last step to get this t completely by itself is to divide both sides by negative 0.3. So I'm going to go ahead and just do that in this step to save myself some space. And now it's time for our calculators. So this would be really ugly to plug in one big chunk, but we don't have to do that. We can do it kind of a step at a time. First, you can type in 1500 divided by 1125, and then from that you can subtract 1, and then from that you can divide 152, and then from that you can take the natural log, and then from that you can divide by negative 0.3. So take your time with this. Don't try to rush through typing it into your calculator. When all of that is said and done, you should get approximately 20. All right, so now on to part B. The question is, what is the maximum number of people that could be infected over an extended period of time? So again, this should ring to you of the concept of an asymptote. So any exponential function is going to have a horizontal asymptote at some point. So we're asking what that maximum is. So we're going to go through the same logic that we went through in the previous example, where we take a look at our function, q of t equals 1500 divided by 1 plus 152 e to the negative 0.3 t. We imagine making this t extremely huge. As we do that, that's going to make this exponent an extremely big negative number. So it'll be like negative 1 million. So in turn, that's going to make this whole expression extremely small because the negative exponent is going to push the e into the denominator. So we'll be taking 152 divided by some extremely huge number, which will make what I just circled approach 0. So our function is going to be approaching 1500 over 1 plus 0, which of course is just 1500. So again, complicated logic, but very simple answer. You just end up with this as your asymptote, 1500 divided by 1, which is 1500. Okay, I want to introduce a new concept here. There is this concept that you might encounter when you're doing your homework problems. It's called the law of uninhibited growth. The deal is, most things in nature do not grow infinitely. For instance, if you encounter a problem that says the population of rabbits doubles every week, that isn't going to be true forever. The population of rabbits can't double indefinitely because eventually there'd be so many rabbits that they would cover the entire Earth and then the entire solar system and then the entire universe. So when we're modeling exponential behavior, we kind of have to just say, all right, let's just assume that growth is uninhibited, even though that's technically impractical. So you might see that in your problems. Don't worry about it. It's just saying we can assume here that the growth will be exponential forever. So that brings us to a specific type of word problem where we're going to have to model exponential growth. And I really wish that I had spelled that correctly. When we model exponential growth, there is a simple formula that we're going to be using. It looks like this. Your quantity after a certain period of time will be represented by a function q of t. Your quantity will be equal to your initial quantity times e to the kt. So your quantity is just your amount after time. Your q naught, or your q sub 0, is your initial amount. E is just the constant, Euler's constant, 2.71. K is a growth constant, or in some problems, it can be a decay constant. And then finally, T is time. This is a standard formula we're going to be using a lot. Now, it's not always represented by Q. Sometimes you might have an amount over time represented by an initial amount, e to the kt, or you might see like the population over time represented by some initial population. So you might see all kinds of variables used, but it's the same concept. The amount which changes over time, the initial amount. All right, so here are some tips for you as you do these types of word problems. Pay close attention to the time units. If the problem deals in minutes, you need to use minutes. If the problem deals in weeks, you need to use weeks. If you don't use the same units, you will get the wrong answer. So pay close attention to the type of time units that they use in the question itself. The second tip is that K, this letter K that's located up in your exponent, this is going to be a constant as well, but we have to find it. It's usually not going to be given to us. It's often the first thing that we want to find in a problem. And then once we know it, it will not change. That constant will be the constant that we use for the entire problem. So we might have to answer subsequent questions where we use the constant as part of our logic to find the answer. The last thing I want to point out about K is that it can represent either growth or decay. When it represents growth, our constant will be positive. When it represents decay, our constant will be negative. So you can use that to kind of check yourself. All right, so I hope that you've written down that standard formula or committed it to memory because we're going to start using it. In this question from the common version of the homework, we've got a wolf population that was decimated, and as a result, the population of rabbits began to grow because the predators were gone. Hey, I'm not the only one who can't spell. If the rabbit population has grown from 120 to 210 in 13 months, ... answer the following question. So this is important. The population started at 120. That's our initial population. The population grew to 210. That's our population over time. And it took 13 months to do it. So that's our time. And notice that time is in months. So let's plug these into the formula. P of t equals P naught times e to the kt. We know that P of t is 210, P naught is 120, and t is 13. We got all of that before we even read the question. The question is, how many months, question A is find the growth rate in rabbits per month. They're calling the growth rate R. We called it K, but they're looking for this number. So part A, we want to find our constant of growth. So all we have to do is solve this for K. That means we're going to start by dividing both sides by 120. So we get 210 divided by 120 equals e to the, we'll call it 13k. Then we're going to take the natural log of both sides to cancel out the e. So on the right, the natural log and the e cancel, but on the left, we'll have natural log of 210 over 120, and that's equal to 13k. Then we can divide both sides by 13, and we get k equals natural log of 210 over 120 divided by 13. Plug this into your calculator, and you should get 0.0430-ish. And they specifically say round to the 10,000th place, so that's why we're taking it out so far. All right, so for part B, we now already know our constant K. So we are going to start out our formula with that constant written in. Once you know K is there for good. So question B says, how many months will it take, so how much time, we're looking for T, will it take for the population to reach 383? So that would be in place over here, 383 on the left. And remember, our starting amount of rabbits was 120. So that goes in for P naught. and then e to the 0.0430t. Now we need to solve for t. So we're going to do all the same steps. We're going to divide both sides by 120. Then we're going to take the natural log of both sides, which will cancel with the e. And then finally we have to, well, let's write this out. Well, 0.0430t on the right. Now we have to divide both sides by 0.043. So we end up with t equals this nasty mess, which you can just plug into your calculator. And when you do that, you should end up with approximately 27 months. We were told to round the answer up to the nearest month, so that's why we ended up with 27. All right, similar problem, but we're going to be dealing with much larger numbers in this example. Wow, this is long. Okay, we're going to have to scroll. When an analyst at a movie studio looks at a graph of ticket sales per day, hint, hint, we're going to be using days, versus days in release for their newest film, she notices that ticket sales drop off in an exponential fashion. So here's another hint. Drop off means decay. So we should be looking for a negative k value. In fact, the graph exhibits exponential decay behavior with a decay constant of 0.3. Okay, never mind. They gave us k. So they told us right here in the problem, our decay constant is 0.3. But they're being tricky. If it's decay, then our exponent is negative. Our decay constant is negative. So they called it a decay constant, but they didn't put the negative on there for you. So you have to make that connection. All right, so let's start off with our function. We'll call this A. We'll call it an amount over time is equal to our initial amount times e to the k t. Well, we already know that k is negative 0.3. And we're told that the film sold 600,000 tickets on opening day. That would be our initial amount. So 600,000 e to the negative 0.3 t. Approximately how many tickets will the film sell on day 8? So they're asking us to plug in 8 for t. So that's all of the information we have. We just plug this straight into a calculator and you end up with A of 8 equals about 54,431. That's it. All right, last example of this video. We are coming up with an expression now. So the function we're working with is f. I'm going to go ahead and write the basic function down. F of t would be equal to f naught times e to the k t. Now let's figure out what they're giving us. We've got a growth constant of 0.16. That's going to go in for k. So f of t equals f naught e to the 0.16 t. And the only other piece of information they tell us is that f of 4 equals 10. That's actually a lot of information. So f of 4 would be f naught e to the 0.16 times 4, because we're putting 4 in for t. And f of 4 is equal to 10. So this is 10. So we get 10 equals f naught e to the 0.16 times 4. And we want to know the initial population. So basically we're just solving for f naught. So we're going to divide both sides by e to the 0.16 times 4. So we would end up with f naught equals 10 divided by whatever this is equal to. Plug that into your calculator. You should get something in the ballpark of 5.27 when you round it to the nearest hundredth. So the question asks us to actually write our function. So we take our function f of t, and in for our initial value we put 5.27 e to the 0.16 t. And that's what we put in as our answer. Okay, so these were on the simple side of the problems. They do get more complicated, but that's why I wanted to dedicate a completely separate video to the doubling and the half-life examples. There aren't very many of those, but they will be presented in a separate video, so stay tuned for the last one.